Hello everybody, today we're going to talk about shaft alignment. What is shaft alignment? Why do we need to have shaft alignment? Shaft alignment is a procedure that if you're a millwright, a maintenance machinist, a maintenance mechanic, if you're an industrial mechanic working in the field, you will need to be able to accomplish shaft alignment. Shaft alignment is a process of aligning one shaft to another, a motor to a gearbox, a motor to a pump, one drive line to another drive line. Reason B is that if your alignment is off, is as if you have hung a door and the door is not plumb, it is not square, and as you open and close it, it wants to rub, it wants to jam, it wants to bind. That is the same principle behind shaft alignment. If you do not have two shafts that are in line, and you're going to have shafts that could be out of alignment in parallelism, which is an offset, or shaft alignment, which is off by angularity, which would be in this configuration. If it's off angular, it's an angle. If it's off in an offset or parallelism, it's offset. Okay, either case is going to be detrimental to your equipment. Your bearings, your seals, vibration. Vibration is a whole nother course in itself. Okay, shaft alignment is key whenever working in the maintenance field and you have a drive, a driver, and a driven. From the driver to the driven, shaft alignment is important. You have sheaves, belts, chains, all of those are part of shaft alignment. And you have shaft alignment itself, which is coupling to coupling, shaft to shaft. And that's what we're going to talk about today. A couple different methods of shaft alignment. You have reverse indicator, you have rim and face, you have the use of using a straight edge. I'm going to focus today on rim and face. The reason being is that rim and face, I believe, is the most easiest way to understand shaft alignment. Get down the basic principles of rim and face and we can move on to reverse indicator. And we're talking about rim and face calculating method. There's rim and face graphing method, there's reverse indicator graphing method, and also calculating method. I prefer the calculating method. The reason being is when you go to graph, you sit there and you draw on graph paper. Then you take those dimensions and you're going to take it and apply it to a movement. And once you take that movement, now you're going to take another measurement, apply it to the graph paper again. To me, there's a lot of steps in the graphing in which you could bypass and focus on the calculating. You take a measurement, you do the math, and you'll see that mathematical calculating of shaft alignment is the quickest and easiest way, besides laser of course, but we're breaking it down to the basics, you guys, using an indicator. The type of indicator we're going to use is a plunger type or a button back. Today, everything I'm going to show you is going to be on theory, on the whiteboard, in which you can go to the field and apply it, okay? And once you understand the principles of shaft alignment, you can apply it to laser alignment, to reverse indicator, to rim and face. All of them have these common components that you have to know and have to accomplish. Is that it is as if you're learning algebra. You learn algebra and calculus, trigonometry, and then you're given a calculator. Do you throw all that stuff out the window? Well, when you go straight to laser alignment, you may not think as if you were doing it from the basic components of using an indicator. And that's what we're going to do. You're going to understand how to take the measurements and how to apply them to your shaft alignment application. Okay, ready to get started. Okay, so in the first process, when you walk up to a pump and motor, you need to understand that there's one component that is movable, which is adjustable, and one component that is immovable, which is stationary. Typically, your pump or your gearbox will be immovable. The reason being is that your pump or gearbox has other components hooked up to it, whether it be piping, whether it be a line shaft, whether it be jack shafts, it's driving something or it's pushing the water. Whatever it may be, usually your driven is going to be a stationary component which has been set up already in the correct position. Your movable is going to be your motor, your driver, Your electric motor is going to be your driver, and that's the one that you're going to have to align to get in parallel and angularity correctiveness to your driven component. Okay, so rim and face. What is rim and face? Rim and face is taking measurements on what is known as the rim and on the face of the coupler. Or you can also use a clamp-on pole device or positioning device in which you have a standard place that you're going to keep your measurements from. The reason being that rim and face has been misused in the past is that people take their measurements at different areas on the adjacent component. You need to take your measurements from the same positioning, meaning that as you turn one shaft, you're turning the other shaft to measure in the same orientation. When you do not accomplish this, what will happen is the runout, the concentricity error of your adjacent component, of your driven component, of your other component that you're measuring is going to impact your measurements, will impact your calculation. Okay, rim and face. So when we take our measurements with rim and face, you have your pump, which is your box or motor, and then you have your movable motor positioning here. The key measurements in which you're going to have to determine, measure, and figure out what they are is going to be your contact point right here, where your face, this is known as a face reading. That's in correspondence to this right here. That's my face reading. This reading of this indicator is known as my rim reading. Okay. Now you're thinking, where's this calculation coming in? The calculation that you need to worry about is going to be with your face. Your face is how you're going to determine your angular compensation. Your angular compensation is an angle, just like it says, angular compensation. Now I got to tell you guys, I'm skipping past a lot to get down to the bare essentials. You also need to understand what is known as indicator sag. Indicator sag, right here, is the amount of sag in which this bar may flex because of the weight of the indicators on that bar. And you're thinking, oh, it can't be that much, a few thousandths. Well, depending on the length of the bar, your indicator bar, and depending on your indicators and your attaching components, your little clamps and shafts, it could be enough to knock it off 5 to 10 thousandths. Okay? So in determining that, as if you were to take this assembly and mount it to a shaft and turn it upside down, you would see, in fact, that it sags down, and it would actually be a negative coefficient. Okay, say it was 10 thousandths. That would be a minus 10 thousandths. Now you're going to ask me, well, what's this negative and positive? When I'm talking about negative and positive, it's a reference to your indicator. All right, I'm focused on shaft alignment, but I'll run through this really quick, is that with indicators themselves, if the plunger, and I'm speaking of a plunger type indicator, moves inward, that's going to be a positive movement. And positive movement means that this indicator is going to rotate, the dial is going to rotate in that configuration. If the plunger is coming in, it's positive. Think about an embracement. When you hug somebody, it's positive. It's positive. That's the same with an indicator. Now, when the plunger goes in an outward configuration, out like punching, that's a negative. So if this was to move in this orientation, it's a negative. It's actually moving outward. So if the plunger's moving inward, it's going to be positive. If the plunger's moving outward, it's a negative. This is important to understand because you're going to have to apply that movement to your calculations when you're doing shaft alignment. Now, getting back to the indicator sag, something that you need to know, I'm not going to focus on this because I want to focus on the root. Indicator sag is a minus adjustment. it's going to be a negative coefficient that you're going to have to deduct from your vertical adjustment. So your vertical adjustment of your offset is going to have to include your indicator sag, okay? The other thing you need to know about is what's known as soft foot. You need to correct soft foot first of all, because soft foot is a improper contact point between your feet and your base plate. If you do not have a flat foundation for your foot of your motor to your base plate, it's going to be at an angle or it's going to be at an offset, meaning that it's not going to be touching at all. So your foot itself, if it's sitting at an angle where there's a gap like that, that would be an angular soft foot. If your foot, your motor, here's your motor foot right here, and here's your base plate. Oh, let me fix this. If this had a gap that was parallel, that would be a parallel soft foot. Either case, it's a soft foot. And you ask me, so how do you correct this? You have to shim it. You have to find your best contact foot. You may have one, you may have two, you may have three that have good contact, or none. None of the feet have contact, good contact. It's not hovering over the part, but a few of the feet are hovering at some point. And how that can happen is from a twisted motor frame, a twisted motor base. A number of issues will cause soft foot. So how do you correct it? You locate your best foot out of the 4 feet, that in which you're going to mount. Find that best foot, snug it. The other feet you're going to shim. Basically, you're going to stuff shims into the gaps that exist because of the soft foot. Now, when I say stuff the shims, you're going to fill the gap. If I have a gap that's an angular soft foot, and say this on this side it's 15 thousandths, and then on this side it's 0.005, I could take a 5,000 shim all the way across it, put a 5,000 shim all the way across the whole bottom itself, and then place a 10,000 shim over here. All right, just to make sure that this does have contact. Now, when I say contact, that means that your foot, when you're looking at it, and here's my bolt in the center, I have to have contact across my bolt's axis. So when I snug it, it's supported on both sides, either on this side and this side, or it's supported on this side and this side. It doesn't matter which side you're using, but you have to be supported across the bolt's axis. It has to be supported on both sides of that foot to have a good register. If you do not correct soft foot and you go straight into your adjustment and correcting for shaft alignment, you are going to chase a ghost, because every time you snug a bolt down, you're actually twisting the frame of the motor. Okay, so soft foot is essential. So let's write this, let's get a little list going here. Number 1, you need to know the indicator sag. Okay, you need to be able to correct for indicator sag. Number 2, you need to correct soft foot. All right, now after you correct the soft foot, you're going to go into what's known as rough alignment. Rough alignment is basically getting your shafting close, okay? You're going to rough in your vertical and your horizontal. There's no calculation involved really. All you're using is a straight edge, checking out what the gap difference is between one to the other. That gap, say it's 100 thousandths, you're going to space all those feet up 100 thousandths. That's on your vertical. On your horizontal, you need to figure out what it is. You can use a straight edge, adjust it to get it close. Hopefully you have jacking shafts on the motor feet, in which it makes it an easy adjustment. If you don't, you're going to be tapping and moving one side to the other side, getting it as close as you can. Once you get it in a roughed aligned area, you're close enough to set up your indicators. when you set up your indicators, you're going to set it up so you have one indicator that's registered on the rim and one indicator that's registered on the face. And the one that's on the face may not have enough room to actually use a plunger type indicator. You may have to use what's known as a button back indicator. Take a look at it. Take a look and see what a button back is. They're more confined. I suggest that when you set up the indicators, you set them up in orientation that you can see the face of both indicators at all times as when you're taking your measurements. As soon as you lose sight of an indicator, you're using a mirror to take a look to see what is going on. Because if you lose sight long enough, it could actually rotate one full rotation, and you'll be one full rotation off from where you think you are, and your adjustments and calculations will be out the window. Okay, so let's go back and make sure that we're all on the same page. We know what indicator sag is, and how do we find indicator sag? We hook up our indicator components on a shaft, we get them dialed up to 0, we just turn it upside down, and we look at what our indicator is registering. It's going to show us a negative value. It could be 5 thousandths, it could be 10 thousandths, it could be a negative 15 thousandths. It depends on how much that rod is flexing. Typically, you're going to see somewhere around 4 or 5 thousandths, depending on the length of the arm. Again, the arm is this part right here. The longer this is extended away from its attaching point, the more leverage the weight of your indicator clamps are going to have. If you're able to attach your indicator clamps closer to here, within a couple inches of that shaft, you're going to have hardly any flex at all, and you aren't going to be concerned about indicator sag. Okay? So, our indicator sag is a coefficient that we have to take into account when we're doing our vertical adjustment. Vertical only, not horizontal. And you don't have to worry about the indicator sag on your face reading, only on your rim reading. Okay, that's your offset. Your rim reading is setting up your offset, your parallelism. Your face reading is going to set up your angularity. Okay? All right. Then we're going to go into the rough. We go to the soft foot, figure out what the soft foot is, correct the soft foot. So now, each foot should be corrected for soft foot. And how do you check that? Well, once you stuffed all your feet, you had one initially that was your go-to foot. That was your good foot. And that one's snug. Now you stuff the other 3 feet. And so basically you have 4 feet like this, looking down. Looking down, and this is our immovable. I'm just showing you looking down on a downward orientation. We're going to say this is my good foot, number 1. All right. This one's solid. I snug it down. It has good contact all the way around. I come over here, and this one needs a 10 thousandth shim on both sides. All right. I come over here. I'm going to write this down. I come over here, this one on this side, it actually needs a 0.005, and on this side, it needs a 0.015. That means I'm going to stick a 5 thousandths all the way across and stick another 10 thousandths in there. On this one right here, I'm going to check it, and this one needs a 0.010, and then this one needs 0.020 across this point right here. All right, so now I'm going to stick a 10 thousandths all the way across, and a 10 thousandths just on that side, in addition to the 10 that already exist to give me my 20 thousandths. If you guys do not know what I'm talking about when I'm talking about thousandths of an inch, that's a topic for another discussion. Okay, number 1. So now we have our soft foot corrected. This one's already snug. We come over here, we snug this one, number 2, number 3, number 4. Torque them to the specification. Whatever size bolt that is, or look at manufacturer's reference, and you'll find what the torque spec is for that bolt in that application with that motor and that base plate. Now we're going to check to make sure we corrected the soft foot correctly. We're going to check each one with the travel indicator, or you could use a plunger type indicator, either or, and a mag base. And you're going to loosen one bolt at a time, and you're going to have it zeroed out. You're going to look to see if it actually moves up any more than 0.02 of an inch. If it moves up any more than 0.02 of an inch, you need to correct it. You're going to have to go in and add more shims. And then if this one moves up, you check and it doesn't move at all, re-snug it, go to the other. It doesn't matter which one you check first, okay? Loosen it and then torque it back down. And you're checking for that movement. We determined that it does not move more than 0.02 for each foot. As we go through each one individually, one at a time, you're good to go. That means you've passed the soft foot. Now you're going to do your rough alignment. When you do your rough alignment, you put a straight edge up here, you check it, and when you check it, you see that you have a gap of 100,000ths. If I have a gap of 100,000ths on my pump side, that means that this guy is sitting high, right? It needs to come down, which could be an issue if I couldn't take it down. So we're going to say the 100,000ths is on this side. When we check with this here, we have 100,000ths. This is going to be lower, okay? In this application, it's lower. So we have to raise it up. We're going to add 100,000ths to each foot. And then we do the same thing with horizontal. We check it with an actual straight edge and we move it into place. That's a rough alignment. With the straight edge, it's not going to be any closer than a rough. All right, you guys, you'll get it pretty close, but I hear guys that's all they use is straight edges. And there's other methods that I could talk about if you do not have the indicators to actually dial it in, but that is a topic for another discussion. We're focused on rim and face using the indicators, the plunger type indicators in which we're talking about. So when I talk about plunger indicators, you guys are going to want to have a set of plunger indicators, a button back, also what's known as travel indicators with mag bases. Travel indicators with mag bases, they will move. You could get from 0 to 1, 0 to 2. They're going to have a movement of a whole inch or a half an inch. 0 to 1, 0 to 1 inch is quite a bit of movement. These little guys, these little plunger types, they're going to move maybe only 1/4 of an inch. Big difference between these moving 1/4 of an inch and the other ones moving a 1 inch, a full travel of 1 inch, okay? These are going to actually be more precision, and that's why you're using these for your shaft alignment. The travel indicators you'll use for your positioning of your motor when you move your horizontal, okay? As you move your horizontal, you start jacking your jack screws or pushing and pulling the motor in one direction or the other. You're able to see how much you're moving it by using what's known as a travel indicator. All right, rim and face. We got through the rough. We have it roughed in. Now we hook up our indicators. We know what the indicator sag is. We have them hooked up. What is key about rim and face? A couple things. One is you need to know the dimension in which the face, this guy right here, is reading. At this point, if you look at this point, it's 4 inch. That means that it's from center line point of the shaft to that point it's registering on the face, it's 2 inches. 2 times 2 is 4 inches. 4 inches is my pitch circle. You need to know that. You need to understand that that is a 4-inch pitch circle on the face. All right? The other dimension you need to know is the bolt center line to center line of your movable in which you're going to adjust. Now you say, why do I need to know this? When you go to check this, the first operation in the shaft alignment, after you have the rough, we're going to move to 4. 4 is going to be your vertical, angular. 5 is going to be your vertical, parallelism. 6 is going to be your horizontal, angular. And 7 is going to be your horizontal, parallelism. All right. Got a couple extra R's in there. Let me take one of those R's out of there. A couple of L's in there. Here you go. Parallel. mix it up. Oh my goodness. I think it's just going to confuse you guys. Here's your immovable, and then here's my movable. Okay, exaggerated. -0.40. Just to straighten that out. Okay, 0 at the top, -40 in the bottom. Now we need to bring this down. You know that this is going to have to come down here. We're going to have to bring it down in the back feet, all right? Or we bring it up. One or the others. It has to go in this orientation. So, how much do we move it? Well, if you look at this, that's generating a triangle, right? That's a triangle. That triangle is going to be the same triangle over here. The only difference is when we're looking at this triangle, you have an angle of theta here. Your opposite, we could say the opposite here, which is going to be 40 thousandths, 0.040 inches, right? And that angle, we need to know how much to move this. How are we going to figure that out? We have 12 inches and we have 4 inches. 12 divided by 4 equals 3. This is going to be our multiplier right here. It's going to be 3. We know this guy right here is telling us that's the difference between these two. From here to here, we need to move this guy 3 times our 40 thousandths. 3 times our 40 thousandths, which is going to be 120 thousandths. So that means we need to remove 120 thousandths from the back feet, or we need to add it to the front feet. That's going to straighten out our angularity. That right there is the hardest thing for people to understand. The key measurements is this point right here where you measure your face, and right here across the bowl. There's 2 triangles here. If this is sitting in this orientation, you can take that and see there's a triangle right here. This triangle and this triangle. They're going to have the same angle to actually get them to be 0. But what we needed to know was, where's this measurement point here? Well, it's at 4 inches pitch circle. Okay? This point, from this point to this point, this is where we can adjust our pivot point of our triangle over here is 12 inches. That's the difference between the two. So if we're looking at this guy right here, if this is, we could go through the math on this also and calculate with this 40 thousandths. We could put the 4 inches right here and calculate the angle and work it through trigonometry. This, which is 12 inches, divided by the 4 inch, that's going to give you a factor of 3. It's going to be 3 times your measured value at your bottom. That is how you do rim and face. The other key component to this is to always take your measurements from the same point of reference on your adjacent coupler, or you're using a pin as a registered pinpoint when you measure with your face and your rim reading. Okay? When I correct the angular misalignment, after we do that, once we correct that, we're going to be sitting in an orientation like this. All right? Now that's what's known as parallel offset. So when we're in a position like this, if we set a 0 here and we come down and touch the bottom of this, and what's going to happen is you could tell from the way this is positioned up higher that this obviously has to come down, right? So how much we come down with it when we're checking our rim reading here, if this is coming and this is attached to my shaft here, as this comes to check my bottom, this is going to go in, which is a positive movement, right? And whatever this positive movement is, let's say it's 0.100,000. It's 100 thousandths of an inch. We're going to move it half. This is what's known as the TIR, total indicator reading. Divide that by 2 will equal our movement. right? So when we check our rim, we come down and we take a look at that, that's going to be our movement. And that's it to rim and face. Hopefully I answered your questions. There's more, there's so much more than that, but I broke it down to the most condensed form and time frame that I have to do this video, and I thank you.